Hi everyone, welcome to the Low Temperature Thermochronology course. My name is Qiang Yu, a geology professor from the Chang'an University, China. I'm glad to be here with you, talking about the chapter 6, fission track dating methodology. In this chapter, 4th section focusing methodology of fission track dating will be concerned, including experimental strategies, sample preparation, external detector method, LA-SAP-MS method. Today, we'll talk about the experimental strategy for fission track dating. Two topics will be introduced as the multi-grain methods and the single-grain methods in this lesson. Let's have a look at the multi-grain methods first. A wide variety of strategies of differing reliability were in use by fission track analysts. Variation between strategies derives essentially from differences in registration geometry and etching efficiency of the surfaces on which the tracks are counted. Two distinct groups of procedures can be distinguished as the multi-grain methods and the single-grain methods, which are shown in the left figure. The multi-grain methods use separate sample aliquots to determine spontaneous and induced tracks. The track counts from each bin summed over the total grains counted. Typically, areas usually of equal size are measured in 100 grains for each track count. The multi-grain methods include the population method and the subtraction method. The population method has been widely used and requires one aliquot to be heated to anneal fully the spontaneous tracks before irradiation to induce tracks in a portion of uranium-235 atoms. The two aliquots are then processed identically and counted sequentially, one aliquot containing only spontaneous tracks and the other only induced tracks. The subtraction method omits the heating step so that the irradiated portion contains both induced and spontaneous tracks. The induced track density being calculated by subtracting the spontaneous density inherently less precise since uncertainties are involved in determining the induced track density. These methods have some disadvantages. With multi-grain methods, both track counts are made on internal surfaces of the same material with identical registration and etching characteristics. However, statistically equivalent uranium concentrations are assumed in two aliquots, which supposes a relatively homogeneous uranium distribution, both within and between sample grains, frequently not true. Multi-grain approaches also assume a single-age population, properly true for a rapid-cooled volcanics, but invalid for samples with multi-age population. Further, laboratory annealing can remove accumulated alpha recoil radiation damage in the crystal lattice, resulting from uranium and thorium decay. This appears to have no effect on appetite, possibly because alpha recoil damage is not preserved. But for zircon and titanite, the etching characteristics may be substantially altered, invalidating one of the principal advantages of the multi-grain strategy. Let's move to the second topic, the single-grain methods. The single-grain methods allow ages to be measured for each suitable grain, even at relatively small sizes that less than 100 micron and are essential for samples containing multi-populations. Usually, 8 to 12 grains were analyzed for each sample. Today, when the age structure of a sample is used to review source and thermal history, many more grains are examined. The repolish and re-etch strategies are variations with a sample repolished, re-etched, and recounted after irradiation to determine the induced track density. These approaches compound uncertainties and are no longer used. In contrast, the external detector method, EDM, has been used almost exclusively as the fission track strategy of choice for several decades. In the EDM, uranium-238 spontaneous fission tracks are etched in the grain, and uranium-235 induced tracks recorded and etched in a detector of low uranium muscovite held against the grain amount during irradiation. Analysis examined the etched grain and its mirror image recorded by uranium-235 induced tracks in the detector, allowing comparison of the identical uranium contents. For the laser ablation inductive coupled plasma mass spectrometry method, although the initial steps ranging from sample collection to mineral separation are common to the EDM approaches, the next practical steps vary a lot. Detailed introduction of these two methods will be talked about in the third and fourth section of this chapter. That's all for the experimental strategies for fission track analysis. Next time, we will have a lesson talking about sample preparation for fission track dating. See you then!